Hello all, welcome to the video lecture. In this video lecture we will be discussing about the image segmentation, and probably this video will be our last video lecture. First of all, we will see some basic image segmentation technique, and then we will see some clustering algorithms as well. Well, talking about image segmentation, it is the process of partitioning an image into different regions corresponding to the objects, and here all the pixels in regions share some common property. We can see here in the image that we can see the simplest property that pixel can share is the intensity, and we can see the different segments of images, like the segmented image the segmented image has, we can see those segmented parts of the image has some kind of same intensity level, or they share some kind of intensity. And there are several types of segmentation technique, but we will discuss only two types of segmentation techniques in our lecture. One is the thresholding based and another one is the clustering based. Now talking about the thresholding, this thresholding is one of the simplest approaches of image segmentation. And here suppose we have image which is represented by 2D function fxy, and we assume that this image contains a dark object against a white background. And in such cases, if there is a dark object against a light background, or if it is reverse, that is we have a light object against the dark background, then we will find that the intensity values they are mainly concentrated near the two regions. And we call them two modes, and one of the region will be towards the darker side, and or we can say towards the lower intensity values, and other will be towards the brighter side or towards the higher intensity value. And if we plot the histogram of this image, we can see here, if we plot the histogram of such image, it will appear something like this. And here we can see this it consists of two peaks, and these two peaks are separated by the dip value. We can see like peak for the background and peak for the object. And as we assume that object is bright, or it may be black, here in our case the object is here we assume that object is bright and the background is dark, so these pixels which are grouped into the lower intensity regions, these belong to the background. Here this belong to the background. It is assumed like it is not from the histogram of our previous figure. We have assumed like it is just the reverse of our previous picture, and these pixels belong to the background, and other group of pixels, they belong to the object. Now the simplest form of segmentation is we choose a threshold value t here, and which is t, and this is where we select is the we select at the dip value region here, just between these two peaks, and take a decision that if a pixel at the location xy have intensity value fxy which is greater than t, then we say that these pixels belong to the object, and whereas if the fxy is less than or equal to t, then these pixels belong to the background. So like any pixels that belong to this above, if the pixel value is greater than t, then we say it is the object, and if it's less than t, then it will be the background. And so this is a simple decision rule for segmentation, and what we have to do is we have to choose the threshold value in the value region, and then check image that the segmentation is simply testing each and every pixel to check whether the intensity value is less than the threshold or greater than that. And this is for the bimodal histogram, or we have two peaks, which means that histogram with the two peaks are the two modes. And however, we can have a multimodal histogram as well, that is histogram can have even uh, more than two peaks, or like this form. Here we find histogram has three different modes which are separated by two different valleys. Here we can see two valleys, and this separates these peaks. And here what we find is, what we can do is we can choose the threshold, say T1 in the first valley region and threshold T2 say in the second valley region. Here T1 and T2 will separate the valleys, the peaks. So what this histogram indicates is that there are three different regions and three different intensity level, three different we can say intensity regions, which are separated by some other intensity band, and these three intensity regions are represented by these three peaks in the histogram. We can see here three peaks. And now the decision rule will be like this, like if fxy, here this if fxy, the intensity value is greater than T2 at location xy, then we say that point pxy belongs to the object O2. Here we can say that if the pixel value at xy is greater than T2 threshold, then we say it belongs to O2. And other is all the intensity values having values greater than T2 will belong to the object O2. In other case, if the pixel value of an intensity, or the intensity value in this region is greater than T1 and less than T2, it is greater than T1, fxy is greater than T1 and less than or equal to T2, then we say that this particular pixel belongs to O1 or object 1. And so the decision rule will be like this, like T1 is less than fxy, which is less than or equal to T2, and it is for xy location, and this pixel intensity will go to O1. And obviously the third condition will be that if fxy is less than threshold T1, if fxy is less than T1, then this will belong to this pixel xy belongs to the background. Here we can have more than two threshold values as well. What we have to do is we have to choose the proper threshold values. And now this threshold operation can be considered as an operation that involves testing against a function t, where this function t is the form of t equal to txy, pxy and fxy, where xy here what we have seen is like, which means that threshold operation is function of xy. This threshold operation is function of xy, and this is the function of and fxy is nothing but the intensity value at the location, and fxy is the pixel intensity at xy, and pxy is the local property in neighborhood centered at xy. Here we have got xy, which is pixel location, and fxy is the pixel intensity, and pxy is the local property in the neighborhood centered at xy. And in general, this threshold t is a function which can be the function of local pixel location, the pixel value, as well as the local property within the neighborhood around the pixel location xy, and any combination of these three, that is pixel location, pixel value and neighborhood property. And this neighborhood property can even be the average intensity values within a neighborhood around the pixel xy. So any combination of so any combination of these three, that is pixel location, pixel value and neighborhood property, gives us this function. And any combination of t can be a function of any combination of these three, and depending on the combination of these, t can be either global thresholding, or we can see here txy can be global thresholding, or it can be adaptive thresholding, or it so in case of t is threshold only for the function fxy, then we say when t is fxy is only for when t is function of only fxy, we say that this threshold is global threshold. Whereas if t is a function of fxy and local property, that fxy that pxy, then we say that the threshold t is local threshold. And in addition to this, t is also function of the pixel, that in more general case, if t is function of fxy as well as pxy, then we say this threshold as a adaptive or the dynamic threshold. So whichever the nature of threshold t, whether it's local or it's global or adaptive, our thresholding operation is by using this threshold. We want to create a thresholded image gxy. Here we have got the gxy, and from the input image fxy we set that gxy is equal to 1, that this gx is equal to 1 if fxy is greater than threshold value t, and it will be 0, gxy will be 0 if that function, if fxy, the given pixel intensity, is less than or equal to threshold t. This t can be global or local or adaptive, and we set gxy is equal to 0 if fxy is less than or equal to t. So here what we have found is that the basic aim of the thresholding operation is to create a thresholded image gxy, this gxy, and which will be binary image containing the pixel values either 0 or 1, and this value is set to 0 or 1 depending upon the whether the intensity fxy at location xy is greater than t or it's less than or equal to t. Now the question is how to choose this threshold value. And now let us come back to the case considering the histogram. Let's see here histogram. We have got the image, and the corresponding histogram is this one. And if this histogram is bimodal histogram, here we have the bimodal histogram, and then what we can do is by inspecting this histogram we can choose the threshold in this dip value. Like we can see the threshold, and if we here we can see like the pixel value range from 0 to 255, and at 127 we can take this as a dip value, or we can take threshold at this 127, and using this threshold we can go for the segmentation operation. Here this is our original image, and after the thresholding we get this we get the segmented image. We have here this is our segmented image, and where the object are dark, here we can see the dark object, and the background is white. So naturally in this case we will have the histogram like this is our histogram. And now if we choose the threshold t, like here we have chosen at 127, and we get this image. And here we can find the second image or segmented image, that our background and object region are clearly separated, and even the shadow in the image, in the original image, is here we can see the shadow, and the shadow is also removed. Here we can see that the shadow is also removed. So this is our original image and this segmented image. Even though they look almost same, but it's the segmented image, and we have selected the threshold value at this dip value. I think we can, if we choose at around 127, then this will give us the very good segmented image. And here we will and here we have seen that the background is also removed. And in general, the image that we get, the input image may not be may not be like this kind, this image, because here we can see that this kind of image we have got a very clear histogram, and we can, after inspecting that histogram, we can just select the threshold value and get the perfectly segmented image. But in general, the input image may not be like this, so we have to go for automatic threshold estimation. So for automatic threshold estimation, what we have to do is we estimate for t. So initially we estimate for t and we choose randomly, and then we segment the image using t. That will produce two sets of pixels, g1 and g2. Like with threshold t, we segment, or we partition the image into two groups, g1 and g2, and from these two partitions we take the average mu1 and mu2 from group g1 and group g2. And now what we do is we compute the new estimate for the threshold, the average of two mean. And what we do is we iteratively segment the image until the difference. Now next what we do is we take take the difference of this initial estimate and the new threshold t, and we iteratively segment the image until the difference is this difference, this ti minus ti plus 1 is like it's less than or some it's below certain parameter t0. We iteratively compute this. We iteratively compute the new threshold and segment the image. And here we can see some of the original image. Here this is the histogram, and we can see here this is the segmented image. This is the original image, this is this histogram, and this is the segmented image by the iteratively estimating the threshold value. So these are for the very specific images. That kind of image we can segment very easily. But in some cases, in generally, the uneven illumination can transform perfectly segmentable histogram into the histogram that cannot be partitioned. We can see here that the illumination pattern is not even. We can see like it is increased gradually, and we can see that this image can be partitioned easily. But because of this, if we use the histogram based partitioning or segmentation, the segmented image will look like this on the right side, which we can see that it's not segmented properly, or it's not partitioned properly. So what we can do is we in order to get the proper segmentation, we divide the original image into sub images and then utilize the different threshold to segment each sub image. Here we can see that this whole image is segmented, is partitioned into the different sub blocks, and we do the same thresholding operation on each subset separately. Here some of the sub images are segmented properly, but still we get some improper segmentation in two blocks. Here we can see these two blocks are still are not properly segmented, and it's because we can see that here if we look at the histogram of this image, and based on the if we segment this based on this histogram, we will get this image like this segmented image. So what we have to do is, in order to properly segment, what we can do is this is the properly segmented, and even we can partition it into the more smaller blocks or histogram small sub images, and we adaptively segment the images. So another um, another segmentation is based on the image segment based on the clustering. And in clustering, the clustering is the task of dividing the population data into the number of groups such that data points in the same groups are more similar to other data points in same group than the other groups, and these groups are known as clusters. And one of the most commonly used clustering algorithm is the k-means, and here k represents the number of clusters. And let's see how the k-means works. And the k-means clustering aims to partition an observation into the k cluster in which each observation belongs to the cluster with the nearest mean. And given a set of observation x1, x2 and xn, where each observation is d-dimensional real vector, k-means clustering aims to partition this n observation into k, or less than, which will be less than or equal to n. And this sets s is equal to s varies from s1 to sk as so as to minimize the within cluster sum of square WCSS. And in the other words, the objective is to find the minimum of the mean and we try to find the SSC, or sum of squares. And a typical version of k-means algorithm runs in this following step. We can see here we set initial cluster seed and which are chosen randomly, and these represents the temporary means of the cluster. We can see here, and imagine that our random number were 60 and 70 for group 1 and 70 for the group 2. And what we do is the squared equivalent distance from each object to cluster is computed, and each object is assigned to the closest cluster. We can see here we estimate the equivalent distance from each object and its mean, and we assign it to this object to its closest mean. And for each cluster, the mean, the new centroid is computed now, and each seed value is now replaced by the respective cluster centroid. And now if we see after the computation, we can see here the new mean for the cluster 1 is 62.3 and the new mean for cluster 2 is 68.9. We can see here its value is changed. And now again the squared equivalent distance from the object to each cluster is computed, and the object is assigned to the cluster within the smallest squared equivalent distance, and the cluster centroids are recalculated based on the new membership assigned. And we repeat this step 4 and step 5 until no objects moved clusters. And in k-means, what we assume is that k-means uses the squared equivalent distance to allocate the objects to cluster, and because the squared equivalent distance is used, the k-means algorithm proceeds to try to find minimum of the error, like minimum for the error sum of squares SSE, and the weak assumption is each group has roughly the same SSE, meaning that the variance or covariance between the objects within the group is equal. So this is the formula for the error of sum of square, and this is the example one, like here. And this is our original MR image, and after k-means clustering we get this. And the advantage of k-means is like it quickly bundles all the n data into k clusters. Limitation is the number of k cluster must be determined in advance. We have to know how many numbers of cluster we will use, and whether or not convergence is highly dependent on the initial central point setting. On the other hand, even if it takes more time, if we need to have a if we need to find the cluster, the appropriate number of cluster according to the data, we should use the non-parametric technique. And the typical non-parametric clustering technique is the mean shift clustering, and we will discuss in detail about the mean clustering technique as well.